yesterday, unfortunately, we weren't able to make it through all the material on lists. So I'm going to pick it up. We covered list slicing, but I think it's worth just touching on again. And then picking it up from here, going through nested lists. So I'm going to try to be super quick about this so we can get through all the material today. We've got quite a lot to get through. So feel free to ask questions. I may or may not take them as they come up. Feel free to ask questions and have conversations about them within the channel. That's fine. Or within the thread for the class today. Okay, so let's touch on slicing again because it's worth talking about. So slicing, if you remember, let's have an example list. I'm going to make just a list with some elements in it. Just have a list of numbers. So I can treat this as like a little archive where I can store these elements and they're bound together in this list. They're just grouped in that list, is what I mean. And I can retrieve elements out of that list again. So I can ask for a certain element by counting its position starting from 0 as the first element, right? So if I wanted to retrieve the first element of the list, who wants to put that in Slack? So if I want to retrieve the first element of this list, that the value of that will be 5. So how would I print out the first element of this list? Cool, yeah. Yep. This will be list sub 0, and that's the way we say it. We'll say sub. So anytime I put in a number, or this will apply for keys and dictionaries as well, but I'll say list sub 0 or list sub 4 or whatever, because the idea with this is that it's like subscripting, or yeah, it's like subscripting in like mathematical notation, or like in a Word document where you'd have like X is a collection of elements, and then you have X sub I with the little I below it, sort of the opposite of superscripting, like raising to the power, right? So this is meant to model that behavior, so we'll say X sub 0. Okay. So that will print me the first element. And I can select any element starting from 0. So if I want to print out that 3, there'll be 0, 1, 2, 3. That'll actually be index 3 there. Oh. Let's do that. Whoops. There we go. Come on. There we go. So that's that 2 now. Just wanted to adjust that so that it wouldn't be the same index and the same value. So that's indexing. Slicing will allow me to specify a starting and a stopping point and get a sublist of the slice that I want. So I'll specify the indices that I want. Let's say I want a sublist that represents this 6 through this 5. So that'll be start at list index 1, 2, 3, 4, 5. It'll go up to 5. That happened again. I'll just make that a 9. Okay, so 1 to 5. So let's just print the slice from 1 to 5. And we're going to see 6, 4, 2, and 3, right? So I wanted up to this 9. I wanted to get up to this 9. But notice that this 9 is indeed at index 5. So 0, 1, 2, 3, 4, 5. So the upper boundary, remember, is not included in the slice. So it goes up to, but not including that upper boundary. Since I want to include it, I'm going to say 1 to 5 plus 1 which is 6. I could do 6, but I'm doing the +1 because it's explicit that I mean index 5 inclusive, right? So it's just to communicate that I want to include index 5. Cool. So that'll be 6, 4, 2, 3, 9. So that's slicing. Let's talk about nested lists. So lists are a collection of arbitrary objects. They are ordered, meaning that you place items in them and those items have an order that's always obeyed. You can mutate lists, meaning you can change their size, you can delete elements, you can add elements, you can, you can move elements around, although that just involves removing them and then adding them back into other places. So you can add elements anywhere in the list, but usually we'll just add them to the end. Usually that's all that's important. So let's look at nested lists real quick. Let's say I have a list, and we'll just have some random values here. Let's just have some integers. And let's have a string. And then let's have another list. And this list can also have a string in it. And then we'll add some more elements after that list. We got too much going on here. Okay, cool. So we just got a list. This is a mess. You know, obviously this wouldn't really be anybody's preferred way of storing information, but this will do for now. So let's say list. Let's print the list. Nothing surprising here. We'll just see the list as we typed it. So let's start indexing into this. So let's say I want to print out this inner list. Well, this is just an element inside its parent list, its containing list. And it resides at 0, 1, 2, 3, 4, 5. So that's index 5. So that'll be list sub 5. So let's say I want to print out this high right here inside the inner list. I can index into the inner list. So look at this, list sub 5 is itself a list. This right here, what I have highlighted right there, that is a list. And like any list, I can subscript into it. So we'll say list sub 0, 1, 2, 3 is high. So list sub 5 sub 3 isolates that one element. Cool. And let's say I want to index from 0 to high here, or slice from 0 to high. I can do that, and we want to include high, so we'll say +1. 0, 1, and high, right? So I can slice that nested list. So it's kind of funny to have these double square brackets, but if you have a list within a list, that, you know, saying list sub whatever number that list is at gives you a list, and you can subscript right into that list. So if we had a list within a list within a list within a list, we could subscript within a subscript within a subscript within a subscript. So that'll work fine. Good. I'm not seeing any questions. Feel free to ask. This is important stuff, so don't worry. I am trying to go quickly, but if there's something that's not landing, do let me know. Okay, so let's have a bit of a breakout. Well, let me make sure this is going to work correctly. Yeah, that'll do. Could I run that? Yeah. That is, it just warms my heart that you said that. Let's run it. So we have list sub 5, which is our list, and then we have a slice into that list from index 1 to 3 inclusive, and that gives us this list right here. Is that what you were asking? Or did you want me to show the super ultra nested mega list? Yeah, you're welcome. Cool. I'm going to put 4 minutes on the clock. Sorry, actually, I'm going to put 3 minutes on the clock. How about it? All right, there's your 3 minutes. Go ahead and put in whatever you got. There's the breakout solution if you want to go look at that. Feel free to put in, if you haven't put in an answer yet, feel free to put in what you've got. Cool, let's talk about mutability. So mutability is an important concept, and it can be a slightly elusive one. Once you get it, it's pretty simple though. So it's easy to kind of juxtapose this against a mutable type. And tuples are a lot like lists, but they are immutable. We haven't covered tuples yet, and I'm not going to get too much into that. So forgive me, I'm going to compare lists to an immutable type that we have covered. So I might use examples with integers and floats and strings. So let's look at something. Let's just say I have x, which is equal to a number. We'll just say x equals 7. I'm going to print x, and then I'm going to print the ID of x. So there's a function called ID, and what ID does is it tells you essentially the ID, the identity that Python uses to refer to that piece of data internally, right? So it's going to generate an ID and assign an ID to that piece of data to the number 7, and that way it knows where that number is. You can think about this like an address in your RAM. It's not quite that, but think about it like a location. Think about it like, you know, this 7 lives in this location, and the location is described by a number. So we'll print out x, and then we'll print out the ID of x. ID is a good function to remember. Okay. Are we gonna run? It's taking a long time. Okay, so we have 7, and then it's ID. So now let's look at something else. If I say x equals x plus 1, well, that's going to be 8. X is going to be equal to 8, and 8's a different number than 7, so it's going to have a different ID, right? So we didn't change. I want you to this is kind of a funny thing, right? But this is an important concept. We didn't change the 7 to an 8. We didn't make 7 into 8. We made x, which was 7 plus 1, which is 8, right? We didn't need to alter 7 to get 8. We still have 7 and we still have 8. Those both exist, but they're both different things. So their IDs are different, right? So with lists, we can change. So here we changed the value of the variable x. You can think about the name itself, x itself, as a pointer, and it was pointing at 7, and then we said, hey, take 7 plus 1, store that in memory, and then point x at that. And that's what this x equals syntax is, right? So this says take the value of x, add 1 to it. That has a different location in memory, and then this is saying point the pointer x to that new identity, or to that new object with a different identity. So let's look at lists. So here we saw the value change and the ID changed, right? So immutable. So integers are immutable. So when the value changes, the ID changes, right? Because something of a different value is a different object fundamentally. So let's make a list. Let's change the value of that list. So we'll have a list. Probably most of you have encountered append at this point. If not, append, there's a method called append. We'll say list.append. And what append does is it's just going to add something to this list, right? So right now this is an empty list. Let's print list and the ID of list, and then we'll append 42 onto that, and then we'll print the value of the list and the ID of the list, right? So this is a little bit different because we're not, notice we're not saying list equals list append, and there's a reason we can't do that. We'll get to that in a second. But we're using this tool append, and append is actually built into the list data type. So the list data type is represented in Python as formally as an object in Python, and objects can have stateful aspects, which are like values, and they can have logical aspects, which are like functions. When an object has a function built into it that references one of the stateful properties of the object, which append does, right? Append references the value of the list, which is an empty list, and it changes that value. So when an object has a function that's built into it that does anything like either references or changes the value of one of the stateful aspects of that object, i.e. its value, then that we call that function a method. Okay, so it's kind of funny, but we'll call append a method even though it's very much like a function. So for now, you can just think about methods as functions that are built into objects. So we'll use this append method, which will add 42 into the list. And now let's see what happens to the ID of the list. And you can think about this, think about like, what's your assumption? Is the ID going to change? Is it not going to change? Obviously, I'm alluding to one of those over the other, but your intuition may tell you something different. And it's good to just write down what that intuition is, or just, take note of what that intuition is. Okay, cool. So these are a little bit out of sync, but if you look at the last few numbers in both of these IDs, we're going to have both of these end in the same few numbers. And that's how you can tell if two IDs are the same. If you look at the end of them, it's easier to see. So both of these end in 6832. These are the same list, right? We didn't make a new list with 42 in it and say, hey, go point at that new list and leave the old empty list behind. What we did is we changed that list, the empty list, into a list containing 42. So notice its value changed, but its ID did not. So immutable means the value changes and the ID changes. Mutable means that if the value changes, the ID does not change. So mutable data structures can have this sort of behavior, but immutable data structures cannot have this sort of behavior. And there's pros and cons to each way. I think some people can look at this and be like, oh, well, lists are obviously super powerful because they're mutable, so mutable types are better. And then they'll sort of expect mutable behavior from other things. But there's good reason for things to not change, right? Like you don't want to you don't want to change 7. Right? Imagine what it would mean to change 7. You can get the result of the operation 7 plus 1, which is 8, but that doesn't change 7 into 8. It just gives you the result of 7 plus 1, which is a different number. So you wouldn't want to like change a number. You wouldn't want to change a Boolean value. That wouldn't make as much sense. Then there are some other data types like strings and tuples that have some similarities with lists. So for example, everything we've talked about with slicing and indexing with lists also applies to strings as well. We can slice and index the characters in a string, and we'll just get substrings. But strings and tuples are also immutable types. Cool. Looks like we got some questions here. So because lists are mutable. The root word here is mutate, the ability to be mutated, right? So lists can be mutated. They can mutate their value without changing the list itself, right? So it'd be like, if I if I take my car in to be repainted, right? Like my car is black. So if I took my car in to be repainted red, they would take my car, which is the same car, and they would mutate the color of the car from black to red, right? They wouldn't like throw my car away and then get a completely identical car with the same VIN number and then, or I guess with a different VIN number because that's the car's ID, and get a different car that's exactly the same except it's just red, right? So they would take my car and repaint it, but it would be the same car. So it's now my car with the color value of red instead of black. So that would be an example of mutability. You take something and you change it, but it's still the same thing. Right, so this is a really good question. This is, I like this question. So this is, so you did get it, I mean, to put it bluntly, to be clear, lists are mutable. The other ones are immutable. So when I say the ID changes, what I'm really, and I apologize because I think I framed it this way, like the ID of this integer changes, and that's not really correct. The ID of 8, which is x plus 1, the ID of 8 just is different than the ID of 7. Those are two different IDs. Therefore, the variable x points at a different object with a different ID. In this case, the variable list, we're not asking list to be pointed anywhere else. And we can see that with this equals, right? We're not asking to point list to some other object. We're just saying, keep the list pointer pointed at the same spot, just change the thing it's have it pointed at the same thing, just change the thing, right? Yeah. Apologies if I'm making this confusing. Yeah, but essentially mutability is the behavior of lists where if the data changes, the ID still stays the same. And immutability means if the data changes, it means it is fundamentally not the same object. Cool. Oh, cool. The little chart for mutable and immutable values. That's great. Good find. Absolutely. Great question, by the way. So mutable would be like how our SSN stays the same even though our age changes each year. Yeah, that's not a bad analogy, right? Like Our SSN is our ID in the program of our government or something. If our government was a Python interpreter, I guess. And then like we change, we change physically and we change in all the ways that I don't need to describe, and our minds change, whatever, but our social security number stays the same unless we go into witness protection program. So I don't know what the analogy, the Pythonic analogy to the witness protection program is, but I'm sure it's out there. The address ID memory does not change for immutable types. Okay, the address, the ID in memory does not change for immutable objects. Well, depending on what you mean by that, I would answer yes or no. If you change the value of an immutable object, it is not the same object. Therefore, therefore you're working with something that has a different ID. But it would be right to say that for that object whose value will be the same, the ID is fixed and associated with that, so it doesn't change in that way. So cool. Why does it matter to us programmers? Oh, the crux of the whole issue. Why does it matter? I would say it matters. It's important to understand which types are going to have what behavior. A little bit ago, I said I would talk about why. So this list.append, I gave this example, like we're not saying list equals list.append. And I wanted to kind of come back around to this. So if you're expecting to change a list by saying, well, when I change something, I say the thing equals the new thing, right? The old thing equals the new thing. Like this may seem sensible. It seems like very sensible code. The thing is, append, it matters in terms of like what behavior you want to expect. So you may expect append to give back a value of that list with the value appended to it. But append does not have a return value. Well, it has a return value of none. So let's look at this. Empty list equals empty list, print list and ID. Oops, we're printing all this stuff. Makes it a little confusing. And then list equals list.append 42, print list and ID. Well, the value of list is now none. And notice it uses a completely categorically different kind of ID for a simple type like none versus a complex type like a list. And there's reasons for that we don't need to get into, but not only are they not the same ID, but they're not even like categorically similar IDs. So that's one thing. It's important to know which types you can manipulate by mutation and which types you have to work with by leaving them in a static form and doing transforms of those. So there are ways of altering, immutable data. I mean, the X example is kind of an example of this, right? Like, oh, I have X. Well, integers are an immutable type. This doesn't mean that like X is always forever going to be 3. I can do a transform of 3, which gives me a new value, but it doesn't change the number 3, right? So if I say X plus equals 1, that's going to change 3 to 4. Well, it's going to change, it's going to change X from pointing at 3 to pointing at 4, but 3 still stays the same, 4 still stays the same. The numbers still are the values that they are. It just changes the pointer of X. So this is like saying X equals X plus 1. So this is sort of this is what we call a transform. So it doesn't alter the data. It gives us a different version of it. I think about it like putting on colored glasses or something. You know, if you put on green glasses, the room you're in is going to look green, but that didn't change the room. It just changed the filter in which you see the room, you know. So a transform says, hey, what would X look like with 1 added to it? Well, it would look like 4. Okay, good. Make that the new value of X. So there's things like that we can do to work with immutable data. It doesn't mean it's like fixed and like rigidly never going to move, but it just means the way you work with it is different. I would say also understanding mutability is important. If you ever get into something where you have to optimize your code, like there are like algorithms that require immutable data structures. So if you've heard of like in-place sorting algorithms, there are different algorithms for sorting something in place versus sorting something out of place. So sorting something in place would be rearranging elements in a list or a collection in the list, right? You're just moving things around until they're sorted in the way according to the rules that you want to sort them by. Sorting out of place would be like, okay, rather than sorting these in the list, I'm gonna like, for example, just, you know, if you were sorting a list of numbers out of place, you could go through, find the smallest number and then put that as the first element in the new list, and then go through, find the next smallest number and put that, and then find the next smallest number and put that, and find the next smallest number and put that, right? That would be sorting it out of place. But it depends, are you removing it from the initial list? Because then you're mutating that list, right? So there's different algorithms that you may learn and encounter throughout your programming career that may require mutable data structures. So it's a great question. Oh my God, the time flies. My, how the time flies. We gotta move. Okay, sorry, I'm gonna cut off questions there, apologies. So copying, so since lists are immutable, we talked about functions the other day, so I'll give an example of this. Since lists have the ability to have their data changed, on one hand, that gives us, that's powerful, right? That gives us more options. Maybe you could make that argument objectively, or at least it seems like it does. It gives us an option that immutable data structures explicitly don't have, which is to change the value without changing the ID. So it's powerful, but you also have to be careful, because what if something changes the value when you don't expect it to, right? So let's say, how should I do this? Def I'm trying to think of an example that's small enough. Okay, so let's say I have a list. I have a function that takes in a list, and it will return an empty list if, or let's just say it'll return, it takes in a list of numbers, and it returns a list of numbers with all of the numbers that were greater than 10 removed from it. Okay, Let's do that. So let's call this remove greater than 10. I don't know. It's a silly function with a long name. So it's going to take in a num list. Let's just pass for now because I'll come back to that. Okay. So our list equals, let's call this my list. My list is going to have 5, 6, 12, 83, 4, 77, that big number, whatever. So I'm going to write a test. My list. And we expect this function to give us a list back that contains 5, 6, and 4. Okay. So remember, we want this function to give us something back. We don't want it to alter the list. Hopefully you see where I'm going with this already, but okay, so let's say well, we're going to get into loops, which we're going to talk about later today. For I'm going to make a loop so I can repeat some process. So I'm going to say for each element in the num list, which is my input here, right? So I take in this num list. I take in a list when I call the function. I call it num list internally in the definition. So I'm going to say for each element in the num list, if L is greater than 10. So if the element is greater than 10, I want to num list dot remove L. And then we'll return num list. This seems like a rational solution to this problem. It seems like it is. Oh no. What happened? Oh yeah. Of course. Ignore this for now. We'll come back to that. Okay. Ignore that bit. I'll come back to that because we're talking about copying and I needed to copy it in order to actually solve this problem in this way. Okay, so the goal was to take in a list and give back a list with all of the numbers greater than 10 removed from it. Okay, looks like we did that. So the question is, what's the value of my list? What's the value of my list? Print my list. Who wants to hazard a guess? Same as original? And 6? 546, or 564, 564. Same as original. Oh, interesting. Yeah, we got a little bit of a split here. I'm not seeing a whole lot of answers. Cool. This appears to have caused somewhat of a conundrum. Excellent. So here we have my list. This is my personal little list. It's just minding its own business, and it's like, oh, well, I think I'll just pass myself to this function, and then the list was never the same. It was altered. It was mutated, some say, beyond recognition. So this actually changed my list. This literally changed that list, right? And if we check this out, let's get the ID What are the IDs going to be? Are they going to be the same? Are the IDs going to be the same, or are they going to be different? Same ID, same ID, same? Nice. Same ID. Oh, wow, look at all them zeros at the end. Cool, yeah. That makes it easy to tell that they're the same. So those are the same list, right? Because if, like, let's trace the path of my list, right? So my list starts here on 45. We pass it to the function on 46. It gets represented internally as num list. And then we say for element in num list, we actually make a copy of it here. So this is not actually the same list on 38. I'm just saying num list copy. Then we alter it here, right? This is the same list. This remove right here, this mutable method call that alters the list, bam, line 40 getting called on my list, my poor, helpless, innocent little list that had no idea what was in store for it. And then line 42, we return it, which we kind of don't need to do, right? If, I mean, we're already altering it, like why return it? You know, but I did that just to kind of throw you off, that this both alters the list and returns it. Now, full disclosure here, I'm hoping it's obvious that this is kind of an anti-pattern. Now, like I said, full disclosure, this is my opinion. I don't want to present this as fact because there are people who will disagree that this is, there are people who say that this is desirable behavior. In Python, I'm going to say there are some times where you might want to write a function that alters its inputs. And by sometimes, I mean not like, well, maybe here and there. I mean like very, very, very rarely. You may consider needing to write a function that takes in an input and literally operates on that input and alters it. And that's because Python has certain limitations that make that necessary at some times. In general, though, you should never do this. You should always avoid writing a function that alters its inputs. I know I just said always avoid it, and sometimes you need to do it, but let me put it like this. You should always, always, always avoid this unless you absolutely know that it's happening and that it needs to happen. You know, if you've exhausted all other possibilities and you've determined, yes, this is the best possible way to do this. In that case, I'd probably name this something like dangerous remove, or like mutable. Like I would probably include it in the name of the function to like remind myself, you know, this is going to alter your input. And I would also include it in a doc string, like some note like warning, this alters its input. So I would go through great lengths to make sure that it was very clear that this was going to alter the list that you're working on. That's just me. This is my preference. Some people are like, nah, it's fine. Do it, whatever. I don't prefer to work that way. I think that can make your code confusing, and it can lead to unexpected behavior. Okay, so why give this example then? So there is a way to do this safely. What we could do here is, let's just call this output list. I'll just call it out list, and I'll say out list. Maybe I could just make a copy of it, right? What if I just made a copy of it and I just altered that and returned that, right? So the way to do that is to say num list. There are several ways to make a copy. We'll use the .copy method. Say num list dot copy. Right here is a different way to do a copy. Notice how this bears resemblance to slicing syntax. This is what's called a full slice, meaning it's a slice that starts at the beginning, goes to the end in steps of +1. What that results in, so a slice always results in a list of a different ID. Therefore, if you do a full slice, it's a de facto copy. So slicing is kind of useful. So I like this syntax and I use it, but .copy is probably what you should use. All of the mutable data types that I'm aware of have this method in them, and they'll make a copy. So now I can alter this copy. Outlist is a copy of numList. So let's run this now. We'll see the IDs of what this function returns. It's no longer mutable, so I don't need to name it that. And we'll see the ID of the original list, and we can see that they're different IDs now. So let's see their values, right? And now we can see that the value of the original list stays the same. So this list, this function is now safe. The list can go into it, it's not going to get altered, and it'll come out the same. Cool. Remove is a method. Yes, remove is a, oh, never mind, you just answered that I just answered it. Okay, cool. So specifically, though, I would say remove is a mutable method. Not all methods cause a mutation, but only methods should cause a mutation. That is, if something causes a mutation, it should be a method, not a function. So yeah. Unless you're writing your own mutable logic that operates on one of the built-in types, in which case you cannot add your own functions. Like or you can't add, I can't, you can and you can't. There's sort of a way you can add methods to Python built-in types, but it's kind of funky. It's a little different. It's not like some other languages where that's really easy. Python has limitations on that, so I would say you kind of can add mutable methods, but yeah. Anyways, so we talked about append, unpacking. Let's just look at this list real quick. So if I say num1, num2, and num3 equals this list, num3, num2, num1. So I can break each of these elements of this list into its own variables, like this. And this is called unpacking. We talked about something similar where I did like A, comma, B equals 1, comma, 3, whatever. This is also unpacking. This is actually unpacking a tuple, which we haven't talked about tuples now. I will probably bring up tuples here and there. For now, you can just think about them as immutable lists. They are lists that have none of the mutable methods, but that's basically what a tuple is. The reason that they're not mutable is they have no mutable methods. So you've seen that syntax before, and we're just saying you can do this with lists as well. We have a breakout here. I'm going to leave this to you to do as part of homework for next time because I want to move on to loops. Hooray. Hooray, loops. I want to be merciful. Let's reconvene at 1 minute after the hour. We'll have a short break. Sorry for keeping it short. Hey folks, there's our minute after the hour. I'll give people 30 seconds to reconvene and sit down and we'll get started. Awesome. I assume everybody is seated and ready to go. Sorry for the short break. Let's get on it. Okay, so shifting gears or switching gears. We're still going to be talking about lists because we're going to be talking about loops. We're going to be focusing on loops. Loops and lists really go together, as you shall shortly see. It was like a tongue twister. We have a breakout. We're going to skip that breakout. Okay, so let's first talk about looping through a list, because often, very often, and hopefully this will be like a kind of a understandable example. Let's say I have a list of objects and I want to go through that list and take each object and maybe examine it, or see if it matches some certain criteria, or do something to it. Maybe it's another list. I want to mutate it. I don't know. So I want to go through each object and perform some process for each object in the list, right? So if we omit the each, let's have our list, and we can say for. Well, these are all numbers, so I think I'll call it num. I get to name this whatever I want, just any valid identifier that you would use for a variable or parameter name is fine here. So I'll just say for num in, and then I'll name something to a collection to go through, right? So list. And then in this case, I'll just print num. We'll just print the num. And you can see I have an example of each number. All right, so 5, 6, 4, 2, 3, 9, 4, 8. Okay, so that's pretty simple. I'm going to show you something that we call the accumulator pattern. And I want to frame this. It's hard to understate the importance of this. Sometimes you'll hear it called the everything algorithm. That's not quite true, but it gets called that because there are going to be days once you get more prolific and when you're going to be coding, you're feeling more comfortable with coding, and you're going to be coding day in and day out for a week or two, and you're going to have the realization like, oh, I feel like I just write various forms of the accumulator pattern all day. Like, it might make it sound boring when I put it that way, but it's kind of nice to have sort of a form that works for so many things. It doesn't work for everything, but it works for a lot, right? And if you think about it, like a lot of problems can be broken down into a list of things and a process to repeat for every item in that list of things. Especially a lot of tasks that a computer can do. A lot of those kinds of tasks humans either don't want to do or they're not good at, whereas computers don't care and are good at accomplishing those kinds of tasks. So I'm going to switch out real quick. I'm just going to switch out this name. Let's call this data list. So this will be my list of data points, whatever. We have a vector of numbers. And then I'm going to call this, I'm going to show you the accumulator pattern, LST. So I'm just going to call my accumulator target LST. So let's say I want to go through my data list and I want to accumulate the squares of all the numbers in data list. So I can say list.append, there's the accumulating, list.append number squared, num squared, right? So where does number come from? Well, remember, number is the element in data list, which is up here. That's this number. Okay. Print list. So now I should have a list of all the squared numbers, right? So 5 squared is 25, 6 squared is 36, 4 squared is 16, etc. Excuse me. And I can wrap this up into a function. Let's say def square nums list takes in, let's call it, let's just call it data list. Actually, no, let's call it in list. I'll need to change this to in list, and I'll need to change this to return list. And then I'll say print okay, cool. So remember the previous example, ask yourself, what's the value of data list gonna be? If I print data list, and I'm doing this to get you thinking about mutability, right? We're working with a list, lists are mutable. Was my input mutated or not? Hopefully not. So think about this. Put it in Slack if you have an answer. Is the value of data list going to have the squared numbers or its original numbers? Guess what? Which way? Squared, original, squared. Data list stays original, 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 original. Okay. Cool. All right. So whether you got it, whether you got it right or wrong, doesn't really matter. Just notice you make an assumption and start thinking about mutability. Thinking about, oh wait, did I change this, right? If you're working with a list, print the list off after you test it. Make sure it's still the same. So this is a way that I can verify whether or not I changed that list. So let's check it out. Okay, cool. So I have two print statements being executed here. The first one gives me the square numbers, and the second one gives me the originals. So why did this one not mutate the list, whereas the other one did? At least in its original form. Well, the way I did the other one, there's something similar about it, but it wasn't really an accumulator pattern. That's kind of one thing about it. The way I was doing the other one, I was removing from the list. I was iterating. I had to iterate through a copy in order to make it work at all. And then I was removing elements from the list, from the input list. Notice I never had something like a copy that I was altering or a target that I was altering. I was just operating directly on my input, and that's the tell-all, right? We have a mutable method. Is that mutable method being called on the input? No. List, we can look at list to verify that it's not being called on the input. So yeah, so this is being called on an object that is initially an empty list. So this is what I refer to as an accumulator target. It's the object being targeted for the accumulation. So we have our loop. Often you'll have conditions inside. Maybe I want to square nums. I want to say only square the number and put it in the list if the number is greater than 4. Right. So there's all sorts of things that I might do in this loop. An accumulator pattern can can grow and become more complicated fairly quickly. This is just a simple one. But at the end of the day, you know, I'm still only altering, I'm targeting whatever process that I'm doing inside of this for loop is targeting, at the end of it, it's targeting this list variable. Cool. So let's break this down a little bit. So we have this for loop syntax, this head of this for loop, and this is going to tell me what object that I want to iterate through and what the name that I want to give to each element in that collection of elements. And then in the body of the for loop, in order to tell it that the code that I want is in the body, apologies because I've been giving examples of for loops, the thing that I want to repeat is tabbed into the body of the for loop. So notice we have this colon. So anytime you see a colon in Python that ends a line like this, you know that the next line better be tabbed in. And if you don't have any code for that yet, you know, you better put in a pass or something until you get some code for it. So we see the colon at the end of the for loop that ends the loop head and begins the loop body. Cool. So this is an example of an accumulator pattern. Now, accumulator, the word accumulator makes you think something that's going to grow in size, which generally I would call that a positive accumulator pattern. But there are other scenarios where maybe you're decrementing a number, or there are cases where you might want to remove from a list, like in the previous one, but you would want to remove from a copy of the input, not the input itself. I would still, even if you're shrinking something, you know, here we're starting with something that's empty and we're filling it up. There are cases where you start with something that's full and you shrink it down. I would still call those accumulator patterns, not because you're adding things in, but because fundamentally there's something very similar going on, right? It still, to me, falls under the heading of an accumulator pattern. So basically what that means in generic form, an accumulator pattern, we start with what I call a target. And I preface it that way because I call it that. That's not a term that I've heard anybody else use, although I've been understood by other programmers when I say it. So if I talk to other programmers, I'll talk about an accumulator target and they'll be like, oh, that's a good name for that. I'm not sure if there's an actual name for what that is, or if I got it somewhere else and thought that I thought of it myself. I'm not sure exactly what that is, but yeah, you can think about this as your target, right? That's the thing you're targeting for the action of accumulation. And then you have your process. So you have to have something to iterate. For our purposes, we have something to iterate through. There are certain cases where you don't know how many times you have to iterate, and there's a different looping structure for that, but we'll get to that later. But for our purposes, you iterate through some object or some amount of times, and you run a process. In this case, it's just 2 lines. Our process is 2 lines. We check a condition. Based on that condition, we perform our accumulation. And then after the loop is over, notice that the return is not tabbed underneath the loop. It is outside of the loop. Then we return the appropriate value. And quite often it's the case that your accumulator target is the thing you wanted to return. I mean, you do all that work to it, it's probably the thing you wanted to return. So this is a very simple and very typical kind of vanilla accumulator pattern that has all of the elements in sort of simple, obvious form. So this is a good example of that. And again, I think it can be easy to undersell the importance of the accumulator pattern. But like I said, There's going to be a day where you're going to be like, oh, I'm just doing this over and over, and it's kind of nice. Kind of makes your job easier in a way, knowing that. Like, oh, well, here's a problem. Well, probably I'll use an accumulator pattern for this. And you just start thinking in those terms rather than like discovering the need for an accumulator pattern case by case. You can just start assuming that most problems are going to be accumulator pattern problems, and the exception is the problems that aren't accumulator pattern problems rather than the other way around. So it's a very useful algorithm. Okay, traversing a list. I didn't really use that term, but that's what we're doing here. When we iterate through, we would say we're iterating through in list. We might say we're traversing in list. For num in list is traversing that list. We're walking through it with num as the identifier for each element. Okay, so let's see. Given the following list of letters, create a function that goes through each of the letter and prints all of the letters if they're vowels. Cool. This is a 6-minute. Oh, here, let me actually pull this whole thing in. So I want you to recall tests for membership as you go through this one. I don't want to do a full 6 minutes on this. I want everybody to give their hand at this. If you don't complete it, that's okay. But I want you to think about it. I want you to, to try to complete it and think about this problem. I'm going to give 1 more minute. Go ahead and do your best. Yeah, like I said, the point of this is to take on the challenge and start thinking about a solution, not necessarily to get a solution. All right. Sorry to cut it short. I'm pasting in my solution. So I decided to write this in a function and do an accumulator pattern. I'm just, rather than, this is where you would print it. But rather than printing, I'm just appending, and then after that's all said and done, then I'm returning that. So I broke the rules a little bit, but I figured since I went through all the trouble of talking about an accumulator pattern, like, here's some context, we can use this and essentially do the same thing. We're not printing every character, but we acquire the character and throw it in a list. So it's a good generic sort of default to go for an accumulator pattern. So they have a bit of a different solution given here, but obviously I, broke with convention on it, so whatever. We've got another one. Let's see here. All right, if given 2 arbitrary lists, write a function that finds the common elements between them. Store these common elements in a list and return that list. Oh, cool. I like this one. Let's do that one too. All right. Have at it. All right, I'm giving us some extra time on this one. I don't see any answers in yet. Well, I see one, excuse me. All right, cool. We can call it there. Let me get my screen share back. Cool. So this is my solution. So given two arbitrary lists, write a function that finds common elements between them, stores these common elements in a list and returns that list. So this is describing an accumulator pattern. The accumulator pattern, we have something we iterate through. We iterate through each element in that collection, and we accumulate or alter in some way some value. In this case, we're just going to alter a list. I didn't mention this, but you can have accumulator patterns with other types of targets other than lists. So you can have integer accumulators and float accumulators and string accumulators. You can do whichever kind of accumulator, but we've just looked at list accumulators. Okay, so I have my accumulation target, my list, and then we have if I say for element in my input, one of my input lists, it literally doesn't matter which one I pick. It could be list one or list two, because we're going to check the other list. So we iterate through one list and we check if the element from one list is in the other list. You could argue, well, how do you know if you're going through the shorter list? Like what if one list has 1,000 elements and the other list has 2 elements or something? This function is not optimized for that. It doesn't really need to be for this purpose, but we could write other logic to handle that. So we'll say if the element is also a member, we'll say if it's in list 2, and the element is not in list. List is our accumulator, so we don't want to add it in if it's already in there. So if it's not already in the list and it's a member of list 2, then we'll append it. Then we return the sorted list. So there's a built-in function that's called sorted that takes in a list, and it doesn't alter the list. It just gives back a sorted version of the list. So this performs a transform on the list, not a mutation. So I did the stretch goals in this to make sure that items aren't duplicated. The way I'm preventing duplication is by not adding them in if they're already in. So if L not in list, add it to list. And I think this is essentially the same. Yeah, this is output, which I'm calling LST, for item in list 1 if it's a member of list 2. So they nested their conditions here, but I unrolled that and did it on one line with an and, which is the same. So just to be clear, what I'm saying is this is the same as if L not in list and nesting that condition in there. So I can get away with doing both of those conditions on one line with an and in this particular case. Accumulators are important. So hopefully I made this clear, but I'll go through this again. An accumulator can be thought of as a running total that is held in a variable. The accumulator pattern, we initialize the accumulator variable, what I'm calling the target, repeat some process, modifying the accumulator or not according to the logic in that process. When the loop terminates, the accumulator will have the correct value. So let's look at a sum accumulator. I gave that example. What if I gave that example where I did a list of the squares of a list of numbers. So what if I did the sum of the squares? So let's say sum of squares. We'll take in a list, and let's do this. Say my list equals list of, just do some random numbers. And we'll say print sum of squares, my list. Okay. Sum of squares. Let's call this now. I could call it sum. You don't really want to call something sum because there's a built-in function called sum. You don't want to override it. It's a bad practice. So I'm going to call it sum underscore. Actually, I'm going to call it total. I'll call it total. And we'll just start total at 0. This will be our accumulation target. That's what we're targeting for accumulation. And then we'll say for L, this is going to be a num, for num in num list. I'll just call it that to remind myself that that's what it is. Has to be a list of numbers because I'm about to square them, so they better be something that I can square, and I can only square numbers. So for num in num list, total plus equals num squared. I'm going to return total. So this is an example of an integer accumulator, of a numeric accumulator. You could use the same logic with, we could have floats in here and then be a float accumulator. So an int and a float accumulator don't differ in that meaningful of a way. So because ints and floats are both numbers, so they're interchangeable in this case. A Boolean flag. So when I talked about accumulators being of different types, like this is an int accumulator, you can have a list accumulator, you can have string accumulator. We call it an accumulator in every case except for Booleans. You can call it a Boolean accumulator. I think you'd be, well, I'd understand what you mean. People on our team would understand what you mean. I'm not sure that everybody would, though. We tend to call it a flag pattern, or yeah, we'll call it we'll refer to this as a Boolean flag, but essentially it's a Boolean accumulator. So if I have how would I do this? Yeah, let's do the simple one first. Let's call this flag equals false, and we'll say for I'm going to iterate through a range, I in range. So we talked about the range function on Saturday. We talked about it with lists because it's kind of related to lists. It doesn't give you a list back, but it does give you something that you can iterate through. If you know how many times you want to iterate through something, range is really useful. Let's say I know I want to run this for loop like 10 times or whatever. I can just do range 10, and then I'm going to have a loop that runs 10 times. This is a range, though, so what it actually does is it gives you items, it gives you numbers, integers, starting from 0 up to, but not including the number that you pass it. You can choose where to start it by passing a second argument. If you pass it 2 arguments, the first argument will be the place where it starts, and the second argument will be the place where it stops. Again, not inclusive, so like a slice. So that upper bound is excluded, just like it is in slices. So let's just say for I in range 10, and let's say, I don't know, let's just have some other variable n, which is equal to 50. And we'll say if I plus n is greater than 100 at any point, then we'll say flag equals true. And then let's print flag. Right, so all a Boolean accumulator is I mean, you have a Boolean flag set to either true or false. It doesn't have to start at false. There are cases where, like, where it starts, there's no like, well, you should always start it at false or you should always start it at true. It depends on what you're doing, where you need to start it and what you need to change it to. So this is a simple Boolean flag, right? We just check some process and we see, okay, well, if at any point n plus I is greater than 100, then we'll swap the flag. But basically, that's the thing. You started it either true or false, and if you started it false, you change it to true. If you started it true, you change it to false under a condition. I think it's safe to say that there's just always a condition being checked that tells you whether or not you need to swap your flag. I will say Boolean flags don't come up that much. One really useful thing, let's just run this. Let's just play around with this real quick while we're here. That's going to be false. So if I do, I don't know, I guess 95, then that'll make our flag true at some point. Cool. Okay. So there's our flag. Let's say we'll do another Boolean flag example here. So let's say I should just grab a list from up here and just grab one of these. Oops. My list equals this, and we'll say for num in my list. And let's say if the number is, we'll say if num less than or equal to 3, then we'll swap our flag. Now, since this is a Boolean value, I can actually use this as a condition. So we'll say if flag, I'm like doing like 4 things at once here. Sorry for my code being everywhere. Okay. Okay, so we need to reset our flag. So if flag is true, then print num to the power of previous num. And let's make previous num exist. Let's create a variable up here. We'll just have it, we don't know where it should start, so we'll start it at none. And then we'll say previous num equals num here. Okay. So this is a little funky, right? There's a bit going on here. But this is what I call a Boolean latch. What this does is it opens the latch under a certain condition, and then the next iteration through the loop, it closes the latch again. So this is going to tell me if at any point, actually this isn't really useful for this particular list. So let's say, okay. So what this is going to do is it's going to start at 5, 8. It's going to encounter this 3. So num is going to be equal to 3, and it'll say if flag is true, that's what it's checking for. The state of flag is true. This is false. It's not going to check that. Nothing's going to happen here. Okay. So remember, num is 3. We're on this 3rd iteration here. If num is less than or equal to 3, so this condition is going to be true, then our flag will be true. and our previous num will be set to num, which is currently our current num. But the loop ends there, so our previous num holds a value of 3, and we end the loop and we come back and we say if flag is now true. So if flag is true, first thing I'm going to do is I'm going to reset my flag just because I want to do that. I want to close the latch so I don't run it again next time. And then I'm going to print, I'm going to do, this is just an example, right? I'm going to do whatever process that I need to do. So there are certain cases where you will encounter something at some point in the list that tells you you need to do something to the next element of the list, or even like further down the list. This will work for the next element. This will tell you, this will give you something to do for the next element of the list, right? So if the number is less than or equal to 3, it's going to print the next number raised to the power of the previous number. We capture the previous number here. We set the flag to true, so that will run it next time. And if you look at this second condition has to be after the first one, and these both have to be ifs. So this problem requires consecutive ifs, because the next number may itself be less than or equal to 3. You know, so we still want to check if that current number is less than or equal to 3, so we can do that to the next number. And if it is, we'll reset the flag to true, etc. Right? So I'm not sure if it's technically correct to call this a latch, because I know there are like logic latches and stuff. So apologies if you know better and I got this wrong. But in my head, I figured this pattern out a long time ago, and in my head, I'm like, oh, it's kind of like a latch. It like opens on one iteration and then closes on the next iteration. To me, that sounded like a latch. So if you need a name to remember this pattern by, full disclosure, it might be a little bit wrong. It's out of my own brain, so apologies. It's just a term that's been floating around for a long time to describe this pattern. So I would remember it, to help me remember it. So this, to me, I think is the case for a Boolean flag. And this is kind of a departure from a lot of other accumulators. It sort of exists in its own way. So you don't see it that much, but it's important to know this is sort of the analogy of an accumulator for a Boolean pattern, or for a Boolean value. Okay, the isPrime function. So this is we're gonna write an isPrime function. And it says, yeah, let's code this together. So fire up your replets. Well, I'll just copy it there. So there's a way to code out the isPrime function. So basically, isPrime, if we write a function called isPrime, it should take in a number and return true or false as to whether that number is prime or not. So if I print isPrime of 4, that should be false, because 4 is not a prime number. However, 5 is a prime number, so that should be true. I'm just going to check a range of numbers, and I'm going to do this in a for loop. So I'm going to actually write my test for this function in a for loop. So I'm going to say for I in range. And when I say code along, I mean this isn't part of the problem logic yet. This is the test, but this is still important. So definitely code this along with me too if you're coding along. So for I in range, and let's just do something. Let's go from 1 to 15. Actually, no, we'll start at 0. We'll do 0 to 15. We'll include 15. You know what? We'll just say 16. Okay. And then we'll say isPrime I. So I've had some people ask me recently what a prime number is. A prime number is a number that has no other factors other than itself and 1. Like 1 is a factor of every whole number of every integer. So a prime number has to be an integer. And every number is also a factor of itself. So, 10 over 10 is 1, 10 over 1 is 10, right? So there's sort of an inverse correlation there. So a prime number has no other factors other than itself and 1. So if you look at the number 7, right, you can ask, well, is 7 divisible by 2? No, it's not. 2 is not a factor of 7. Is 7 evenly divisible? I should specify that it means evenly divisible, right? You could divide 7 by 2, but you don't get a whole number. You don't get an integer value back. So is 7 evenly divisible by 3? No. Is it evenly divisible by 4? No. Is it evenly divisible by 5 or 6? No, it's not. So we know 7's obviously going to be divisible by itself. 7 over 7 is 1. 7 over 1 is 7. It's going to be divisible by 1 in itself. So we're not going to count 1 in itself. So it's just a number that has no other factors. So let's say def is prime. We'll take in a number I'll call n. And then, I'm going to guess. I forget whether I need to start this as true or false. I'm just going to guess it as false. If I need to start it at true, that'll become obvious when we get there. So let's say I'm going to do what I just did. I'm going to imagine that n is 7, and I'm going to write an algorithm that does exactly what I just did. I'm going to start at 2, because if I start at 1 and check if 7 is divisible by 1, it's going to be divisible. So I don't want to do that. I'll start at 2. We don't need to check 1. So I'll say for I in range. I suppose I should specify this. Usually when we're iterating through a range, it's conventional to just call the number I. Think I for index or iterate or integer or something like that. So it's there's a standing convention around calling it I. You can call it num or divisor or whatever, but I'm going to call it I. So for I in range, we'll start it at 2 to n. We don't want to do +1. We don't want to include n. We want to exclude n because we don't want to divide it by itself or 1. Otherwise, that'll throw things off. And then we'll see if n is divisible by I. And the way we can do that is we'll say if n modulo I. So if we divide n over I and we get a remainder of 0. So n mod I equals 0. Then we'll say prime, we'll flip our flag. We'll say prime equals false, right? So since I said flip it, that means we need to start it at true here, right? So this is a good example. Like there's a lot of times where I'm like, I don't really know where I need to start this. I'm not going to waste my time thinking about it. Like I'll just dig into the problem and I'm sure it'll become obvious, like what I need to do once I'm in the problem. I've written this problem this way so many times and I can still never remember. But you don't need to remember. You know how to find out. And then if we make it all the way through this loop and we never set prime to false, then it'll be true. So we'll return prime. We have an edge case here because this range doesn't check numbers. Like what if n is 1? What does it mean to have a range from 2 to 1 or 2 to 0 or even 2 to 2 if 2 is excluded from the upper boundary but included in the lower boundary? So that's actually going to mess with our for loop. We will still have valid code. It won't throw an error or anything, but it's just not going to run this loop. And it'll, for numbers that are 2 or less, it'll just always return true. 0 and 1 are not considered prime numbers. So we need to take an edge case here and just say if n is less than 2. less than but not equal to 2. Then we'll return, we'll set prime equal to false. Cool. So let's see what our output is. Remember, we're checking every number between starting at 0 all the way through 15. So I'm going to just print I next to this so we can actually see. Okay, cool. So 0 and 1, remember, are not prime numbers. 2 is a prime number. It's the only even prime number. 3 is a prime number. 4 has a factor of 2, so that's false. 5 is true. 6 is not a prime number. 7 is 9. 8, 9, and 10 are not prime numbers. That's good. 11 is true. 12 is false. 13 is true. 14 and 15 both have factors, so they're false. So this appears to be working as expected, unless you see something that I don't. Cool. So I don't prefer to solve this problem with a Boolean flag. I prefer, I'll just juxtapose this. I think it's easier to just, as soon as you know what value to set prime to, just return that value instead. So we'll get rid of the flag, and then I'm going to do this. Return and return, true. So this is what I prefer to do. I think this reads a little better. I think about it a little better this way. We say if n is less than 2, then just return false. 0 and 1 and negative numbers, we're just not going to worry about them. They're just not prime numbers for our purposes. So for I in range 2 to n, if n is 2 or greater, we check every number in that range, see if I is a factor of n at any point. And if it is, we don't need to set the accumulator or the flag and then keep looping. We can just say, we can just return false right there. And that's going to stop the loop midway through, since a function will stop executing code once it encounters a return. So if at any point I is a factor of n, it just returns and stops executing code. If we make it all the way through this loop without returning false, then we just return true. So that's the way I like to do this, but sort of pick whichever way. If you can do it reliably the other way. I find this way to be honestly a little harder to think about, because I gotta like guess where to start that. But I don't know. If it works for you, do it. Cool. Is prime. List accumulators, we already talked about those. Loops as filters. Oof. Yeah. Break and continue. We talked about pass, so we're not going to talk about pass. We've only got a couple more minutes, but let's just cover break and continue real quick. The loops as filters thing, I think, is a pretty natural kind of consequence of the accumulator pattern. You can loop at that slide if you want to, but yeah, it's pretty straightforward. So break and continue. So let's look at our isPrime function again. Like I said, one of the reasons I prefer to do return, here, I'll just actually uncomment this. One of the reasons I prefer to return is, imagine I'm checking some super large number that is a prime number. Let's say, shoot, I don't know any huge prime numbers. Let's say I'm checking some prime number that's over like 10,000. And I find that it has, or let's say I'm checking a large number that's not a prime number. Let's say 20,000. 20,000 is divisible by 2. So this is going to start with I equaling 2. I's first value will be 2. And in the Boolean flag solution, it says if in mod I equals 0. So if n over 2, if 20,000 over 2 equals 0, which it does, then we're going to say prime equals false. Then we're going to do 19,997 more iterations. We've already determined that it's not a prime number. We don't need to do any of those iterations. But one of the advantages of the return way is, like I said, as soon as the function encounters the return, it returns this value and it stops executing code. Even if it's in the middle of a for loop, it doesn't do any more iterations. It doesn't run the next line of code. It just stops. That function's over, right? It gives you the value back and that's it. So this saves you from unnecessary loopage. If you want to do the isPrime way, we can stop the loop manually. We can say, okay, we've determined it's not a prime number, break. So break pertains only to loops. There are two types of looping structures. We talked about for loops today. There are also while loops. We'll get into those in a later lesson. But break pertains to for loops as well as while loops. And all it does is it just means stop the loop. That's all it means. It's like saying stop, right? So it just says stop, no more iterating. Break is good if you encounter a condition. You'll usually put it on, I would say, well, you'll always put it under a condition. You don't just want to have it just in the loop because then you're only going to get one iteration. So you'll have it under a condition and you'll check the condition and you'll be like, well, if this condition is true, then we can just, you'll usually do something else and stop the loop. Sometimes you'll just stop the loop. But that, in this case, we can just stop looping because we found that it's not a prime number. Continue is something similar, and unfortunately, we're slightly over time. Continue just skips one iteration of the loop. So continue, you can check a condition and then move on. You can run a continue line and it'll move on to the next iteration, right? So it won't execute any more code in that iteration, but it'll keep looping. It'll just skip that iteration. There are certain problems where I want to iterate through some collection, but I want to like skip the first iteration or the last iteration. So I'll say if the index equals 0, we're on the first iteration, and then I'll just skip that. I'll say continue, and we'll move on to the second one. And sometimes that can save you some work, but we'll get into more examples of that later. Sorry to kind of rush through the last of this, but break and continue are kind of straightforward. We have some more breakouts. I'll just assign those. I'll roll those into the homework for next class. Yeah, that's it. Sorry for going over time. I'll try to do my best to curb that in the future. But yeah, have a good rest of your night. And feel free to stay on if you have any questions.